Last week we learned about basics of continuity. First of all, continuity at a point, continuity in a interval. Continuous means there is no breaks in the graph. That is geometry wise we can speak. We can draw the graph without break at that point or in the interval. That is continuous, right? Mathematically, if we speak, approximate value in the neighborhood of a must be equals to the function value, right? That is limit x approaches a, f of x must be equals to f of a, right? So that is what we say continuous function, right? So like now at one point we have learned, now that thing we will apply to the interval. If it is continuous in the open interval a to b at every point, right? So and at a it is right continuous, at b it is left continuous. Then we will say the given function is continuous in closed interval a to b. Then like on the domain and on a set of real numbers we have learned, there are some standard functions which are continuous in their domain or which are continuous on our set of real numbers. Clear? So like I think in last class we have solved few basic examples about this continuity thing. Right? Like I can tell you one thing in continuity and differentiability and this definite integration, they'll test you how well you can break this modulus function, how well you can break this greatest integer function, how well you can tackle this fractional part function. If you don't know about them, like please go and revise once or learn once, right? If you need any help, you ask me, maybe we will have one class or something, right? So like if you are not good in breaking them, definitely you are going to struggle in continuity and differentiability, right? Second thing, you have to be good in this graphical transformations, right? In 11th grade functions you would have learned graphical transformations, right? So graphical transformation, if you are not good, like some problems can be solved using graph easily. If we are trying to break it, it might go lengthy. Clear? So like graphical transformation is also important. Two main things I can say. uh, so then today's class we are starting with this uh, one small uh, what like I think in last class I told with conviction here g of x is equals to greatest integer of f of x will be discontinuous. When I went home and checked it again, there are some points where even though f of x is continuous and like greatest integer f of x is integer, function is continuous. So like I rephrased it little bit. I suggest everybody to change this and then below one as well. G of x is equals to greatest integer f of x. I looked it again, I gave earlier, will be discontinuous. It is not always, not will be, we should write can be, may or may not be is also okay. Can you make that small change for greatest integer of f of x and then for fractional part of f of x? These two can be discontinuous. If you read it again in bracket, I wrote need to verify at turning point. What actually this turning point is? I think you would have known about increasing and decreasing nature of a function. If a function is changing its nature from increasing to decreasing or from decreasing to increasing, that is called as turning point. At that point, we need to check very carefully. Clear? Understood this one? Any doubts in this? Anybody? Right? So like this is what I want to correct, and then remaining I kept as such. If anything I missed out of this last time I didn't give, you can write signum. Okay, add signum. Signum will be discontinuous whenever f of x is equals to 0. Right? Am I clear? Call might be affected. Why? Internet. Are we done in this? Can we move to the next one? So in next, right? So this is about algebra of continuity. If you see NCRT, like they have given only when f and g both are continuous. Remaining they didn't give. I have seen some reference books and then I have like gathered some good counter examples to justify my reasons. Right? So like I'm going to explain it. First you listen, then you can write it. When we have two functions f and g, right? This is purely about at a point. At a point A or at a point C we are speaking. When we have two continuous functions, you add them, subtract them, multiply them, divide them, and denominator is non-zero, right? Multiply with some scalar and then like take power n. These all things you do. Composition also. The resultant will be continuous at A. Clear? So like now, let us tweak little bit. Instead of taking two continuous, one is continuous, another is discontinuous. It can be anything. So what I wrote f is discontinuous, C is continuous. It can be vice versa as well. Clear? So in that case, what happens? I can say that when you are adding one discontinuous function and one continuous function, clear? So you will get discontinuous there. Clear? And then like subtraction also same thing. Clear? Now the last multiplication if you do, n stands for need to check. Need to check I mean it may be continuous, it may be discontinuous as well. Composition also same thing. Am I clear? Right? So when both are discontinuous, I didn't swap them. Same thing only I should write. If I write f continuous, g discontinuous, same thing only I should write. Clear? When both of them are discontinuous, in that case like add them, subtract them, multiply them, do the composition, we cannot say anything. Right? Need to check at that point. May or may not be continuous, or we can also say may or may not be discontinuous at that point. We have some good counter examples I have taken that we will see to justify this argument. Please copy this table. Understood? Right? One thing should be in our mind when two continuous function we are doing all algebraic things, the resultant will be always continuous. When one is changing, one is discontinuous, other is continuous. In that case, we are very much sure about their sum and difference. Remaining need to be verified. Right? Understood this one? Copy this one. After this, we will see some good counter examples to justify these reasons. Right? Are we done in this? See, like I wrote below also what is C stands for, what is D stands for, and what is N stands for. In need to check case, you can write may or may not be continuous. Maybe we can also write may or may not be discontinuous. That we cannot say anything without verifying. Right? Are we done in this? Can I scroll up? Right? So I am scrolling up. Now counter examples. Like we are starting our counter example for this one. Like if you want any example, one continuous, one discontinuous, that we can give proof. Like you take x, you take greatest integer, subtract them, you get fractional part, that will be discontinuous at all integers. Clear? So like now this one, like again if you want any function which you are taking like one discontinuous, one continuous, their product you will get easily discontinuous. But I'll give you one counter example where it will be continuous. Clear? So like, yes, please. So in counter example one, let f of x is equals to x and g of x is equals to signum of x, right? So we can say f of x is continuous at 0, signum of x is discontinuous at 0. So that one also I'll write. Right? So like if I multiply them, what I am getting? F of x into g of x will be equals to x into signum of x here. So if I use the definition of signum x, I'll be having like minus x when x is less than 0, 0 when x is equals to 0, x when x is greater than 0. Now if you check the left hand limit at 0, how much we are getting? If we check left hand limit at 0, how much we are getting? Right hand limit is function value is right. So what I can conclude, therefore f of x into g of x is continuous. Yes, please. At x is equals to 0. Product of one continuous and one discontinuous may or may not be continuous. We can also add may or may not be discontinuous. Clear? Understood this one? So like to justify this argument, we will say one a note point here. Like this is not for all continuous and discontinuous function. We have some type here that we will write. So that one is like if f of x is continuous at x is equals to a and f of a is equals to 0, g of x is discontinuous at a. Yes, please. So we have taken two functions in such a way. First function is continuous, function value is 0. Second function is discontinuous. In this case, then f of x into g of x will be continuous at x is equals to a. This is what I used in last class as well. If you remember, there we are doing continuity for x into greatest integer x by 2. So there I have taken only 0. Few of you asked why sir only 0. There I told like we will see in upcoming classes. This is what I mean. One continuous function and then another is discontinuous. Function value at a is 0. Then their product will be continuous. Clear? Understood this one? Any doubt in this? Now second counter example will go. In second counter example, I think, can I scroll down? I want to check here. I think I have given one counter example for this. Right? Then the last one we will see. Same. One continuous, one is discontinuous we will take. And the resultant will be continuous. Clear? Can we go there? So like this is second counter example. Yes, please. So let f of x, okay, one continuous we need, okay, signum down, okay, right. So I have taken one small example, let f be a signum function, g be a fractional part function. So now I am doing the composition here, right? We can clearly notice if we want, we write. Maybe let us do the composition and justify this. F of g of x must be equals to how much I'll get? I'll get signum of fractional part of x, correct? Signum of fractional part of x. Now tell me what I'll get from here. If I do the composition in this way, what will be the output for signum of fractional part of x? 12th. Signum of fractional part of x. What will be the output? 0 or 1. Am I clear? When x is 0, you will get 0 output. Right? Or some integer you are giving, you will get 0 output. Some maybe let's say, one moment. Non-integer we are giving, what output we'll get here? 1. Just give me a moment. No, sir, this is SW. That room, I think, sir. I don't know, sir, then. Opposite room, you check, sir. One moment, like, this one seems not working. Composition, let me do later. So, like, let us take two discontinuous function. Composition, like, let me do later. Let us take two discontinuous function. I'll add or subtract them. I'll get one continuous. So, let f of x is equals to greatest integer x. G of x is equals to fractional part of x. Two discontinuous function at every integer. So, if I'm adding f of x plus g of x, I'm going to get here x. Clear? So notice that f and g are, one moment please, discontinuous at x is equals to 0, I can say, but f plus g is continuous at x is equals to 0. Understood? Right? Which one you want me to scroll up? No. That one I removed. Like that seems not working. I need to look for some other one. So like maybe let us multiply and get a continuous function. Yes, please. One moment, I'll explain. Okay, like somebody having doubt why f plus g is continuous. Fractional part of x and then greatest integer. If you substitute here, you will get x minus greatest integer x. This will get cancel, only x will be there. X is a polynomial function. It is continuous everywhere. Clear? That's why only we will say f plus g is continuous. Now, in next counter example, we have taken two functions, f and g. You can clearly see both f and g are discontinuous at 0. Now, if we multiply them, we are getting f of x. Then let us change 1 here, minus 1 here. F of x into g of x. What are we going to get here as, please? We will get, like, multiply there. Minus 1 only will get, not 1 and minus 1. This will be minus 1. Again, notice that f plus g, f and g are discontinuous, but the product is continuous we got. Clear? Any doubts in this? I think like I have given the counter examples for addition, subtraction and multiplication thing. Now we need to look for this composition. Composition is like slightly trickier. So don't worry much about the missing part that we'll upload in the Teams. You can get the notes from Teams. Try to focus from this one, right? So like now composition, we are thinking we should take like two functions. One must be continuous, second must be discontinuous, and then the composition we should get as continuous. Here, can I scroll up? Right, everybody copied this one? No, right, please. So like in this short time, can anybody think about that kind of counter example? One composition. One function is continuous, another function is discontinuous. We are doing composition between them. We should get continuous function there. At one point, you tell that will do. Okay, like maybe I have same example. I can use that. Can I scroll up? So scrolling up. I hope everybody following this class and understanding. Now, in fourth, let us take a function f of x is equals to fractional part of x, g of x is equals to signum of x. Maybe this will do for us. If we take the composition between them, f of g of x, we will get fractional part of signum of x. Yes, please. So how much is fractional part of signum of x? 0, right? So we get 0. Notice that, right? We can see here, one is JE class. Like at 0, if you take, will you agree with this statement? Here, F and G both are discontinuous at 0, right? Maybe we will, okay, one moment. Discontinuous at 0, but f of g of x is continuous at 0, correct? Now, like as I said, one must be continuous, one must be discontinuous. For that, I can write in this way. Yes, please. I can rephrase this one. Here, f is discontinuous at x is equals to 1. Fractional part is discontinuous at x is equals to 1. G is continuous at x is equals to 1. Signum is continuous at 1. And then like what we got, f of g of x is continuous at 1. That you can clearly see, that is a constant function. Constant function is continuous everywhere. Any doubt in this counter example? Right, for both of them, I have given only one counter example. One is signum, another is fractional part. Right? Any doubts in this? Understood? Copy this one. This is about counter example, right? When one of them is discontinuous, we can say about f plus g or f minus g will be discontinuous. A remaining need to be verified. When one of them is discontinuous, the composition also need to be verified. We might get continuous, we might get discontinuous as well. As I said like earlier, there will be some functions where like last class thing, greatest integer of f of x may be continuous even though f of x is equals to integer at some point if it is a turning point. For that, one example I'll take. Can I scroll up? Everybody copied this? Understood these counter examples? Any doubts online, offline? No doubts, right? Now let us take a function f of x is equals to greatest integer of x square, right? So greatest integer of x square, if you notice, y is equals to x square will be decreasing till x is equals to 0. From there, it will be increasing. Clear? So at x is equals to 0, it has a turning point, and then x square will be integer when x is equals to 0. Correct? So like now if we check the continuity, like left hand limit x is approaching a 0 minus f of x will be equals to limit h approaches 0 greatest integer of 0 minus h whole square, right? So we will get this one as limit h is approaching 0 greatest integer of x square. You can directly substitute here, you will get 0 in this case. And then right hand limit x is approaching 0 plus f of x will be equals to limit h is approaching 0 greatest integer of 0 plus h whole square, and then you can see this will be limit h approaches 0 greatest integer of h square. So that is again 0. In another way, what I can say is you take minus 0.1 for left hand limit. Square you do. Positive it is. In between 0 and 1, you will get 0. Plus 0.1. Square again in between 0 and 1. Greatest integer value is 0. So like here, limit value is equals. That means LHL is equals. RHL is equals function value at 0. Right? As I said, this is another counter example when function has turning point. Again, continuity need to be verified. Understood this one? Any doubt in this? This is about algebra of continuity. Right? The table what I have given, keep that one in your mind. And then next we are going to see about why the discontinuity arises, the reasons of discontinuity, and then the types of discontinuity. If time allows, we will see the differentiability as well. Once we finish differentiability, then problems will be mixture. In one problem, they will say like m be the number of discontinuous points, n be the number of non-differentiable points. So like both put together, if we learn the differentiability, then we can solve it. Right? I just want to know anybody who didn't give exam here yesterday. Can you raise your hand if you didn't give exam yesterday? Remaining all give. Okay, hands down. Just I want to check. Oh. Shivakumar S is also raising his hand. Why, dear Shivakumar S? Why you didn't give exam yesterday? Oh, you already gave one exam. UT2. Okay, it's up to you. Are we done in this? So let us go up. Reasons of discontinuity will be the subheading, and then let us learn about it. So in reasons of discontinuity, there will be some functions. Limit at that point will be existing, but function value may not be defined. Clear? That is one reason. Second reason is like limit exists. Function value is also exists, but limit value is not equals to function value. That is second one. Third one is like limit does not exist. Both are finite but does not exist. Fourth one is at least one of the left hand limit or right hand limit is approaching infinity. Clear? So four main reasons we can say here. Reason number one, limit at a exists, but f of a is not defined. If this is the reason of discontinuity, this we can make as continuous function by redefining it. If we need any example for this, we can take limit, not limit, function I should write f of x is equals to x square minus 1 divided by x minus 1. Function is not defined at 1. Clear? Understood? Right? This function is not defined, but limit value exists. Second reason, limit at a and f of a exists, but limit x approaches a, f of a is f of x is not equals to f of a. So this one also we can redefine it and we can make it into continuous, right? So like first one we call as missing point discontinuity in types we will see. Second one we'll call as isolated point discontinuity. Now the third one, both left hand limit and right hand limit are finite values. Yes, but left hand limit is not equals to right hand limit. Whatever you do, this you cannot make into a continuous function. Yes, please. No, that we will write later. This is reasons. Later we'll write them. Fourth one, at least one of the LHL or RHL approaches to infinity. This is another reason. So mainly we can say limit exists not equals to function value. Both like limit exists, function value does not exist. Limit does not exist. Last two cases, limit does not exist case. We can make into continuous. Right. Then next is types of discontinuity. Mainly two types: a removable type, non-removable type. We can remove the discontinuity that is removable. We cannot remove the discontinuity that is non-removable. Clear? Can I scroll up? All copied this. Types of discontinuity. Types of discontinuity mainly two types: a removable and a non-removable. A removable type and non-removable type, they will say this is discontinuity of first kind. Second one is discontinuity of second kind. In removable again you have two types. In non-removable you have three types. Right? So like maybe I'm telling here, I'm not giving the definition for removable and all. Limit exists not equals to function value. That is removable. Limit does not exist. That is non-removable. Clear? So, by redefining the function that we will see now. Right? In this case, f of 1 is not defined. Listen here. F of 1 is not defined. I can add the value of f of 1 as same as limit value. What is limit value in this case? 2. So like f of 1, I'll make it as 2. Then it is continuous function. That is what we can make continuous mean. So in removable type, missing point is the first one. Missing point means, please write there, limit at a exists, but f of a does not exist. This type of discontinuity can be removed by redefining function value. So example, maybe let us change f of x is equals to x square minus 4 by x minus 2, x not equals to 2. So here f of x has missing point discontinuity at x is equals to 2. Now by redefining the function, let's say g of x is equals to function f of x when x not equals to 2, and how much is limit value at 2? I think 4 I'll get 4 when x is equals to 2. Now if you notice here, we can see g of x is a redefined function which is continuous at x is equals to 2. Understood my point? Any doubt in this? Anybody? Sorry? No, like I'm redefining the function in such a way it is continuous. F of 2 is not there because 2 is not in the domain. So I redefined it so that I am assigning some value at x is equals to 2. Sorry, we are including 2. Clear? Any other doubts? Understood? Right. Even though you simplify, since x minus 2 is there in the domain, denominator, equals 2 won't be there in the domain. Clear? So next is isolated point discontinuity. Second one, this one in removable type, that also we can make as continuous. Oh dear, you are all too early for next class. Sorry for being early. So I should punish you for being early. Can I scroll up? All done in this? So isolated point discontinuity. Isolated point means you write the reason, limit exists, function value also exists, but both of them are not equal. Clear? Limit exists, function value also exists, but both of them are not equal. Again, by redefining the function, we will make that one as continuous. Why we make them as a continuous? To read about the function more in detail. Clear? See, like in NCERT or some books you will see, no? They will give function f of x is equals to piecewise they'll define sin x by r like 1 minus cos x by x square when x not equals to 0, and some k x is equals to 0. That is redefined function. Technically 1 minus cos x by x square is not defined at x is equals to 0. Right? We to study about the function at 0, or like to study about the nature, we redefine it. Yeah. So this type of discontinuity can be removed. So I think let me give you an example here. F of x is equals to signum of fractional part of x. Signum of fractional part of x will be equals to 0 whenever x belongs to integer. Or else how much we get? Or else how much we get? Signum of fractional part of x will be 0 when x is an integer. Or else 1, yes, perfect. Otherwise 1 when x does not belongs to integer. Right? So at every integer, the function is discontinuous. Now, how we can make this function continuous? F of x is discontinuous at every x belongs to z. How we are redefining it? We are writing or reassigning g of x will be signum of fractional part of x when x does not belongs to integer, and then it will be 1 when x belongs to integer. Now this is continuous function. Again, there are two types of removable type discontinuity. One is missing point. F of a is not there, right? Because a is not in the domain. Second is like limit exists but f of a is some other value. By reassigning f of a value, we can make it continuous. Clear? Now we will see about non-removable type. In non-removable type, there are three. One is finite, another is infinite, third one is oscillating. Finite means LHL, RHL is finite, but both of them are not equal, right? Infinite means at least one of them is infinity. Oscillating means it is, we know definitely some finite value, but we won't be able to find that limit. It will oscillate in between that two finite values. Clear? Can I scroll up? All done in this? Eh, We are redefining the function definition at the integer so that we can make into a continuous. Uh, where we use it? Why we are doing it? No, like it is not about the same function. Like we let me look again. I am exactly not sure where we will use, but like in order to study that kind of functions in detail, we will redefine it and we will make it continuous. For some function like to be differentiable or to be integrable or like anything like that, function must be continuous at that point. If I remember correctly, like they are making these functions continuous to find about like to know about its derivative, about its increasing, decreasing nature, something like that. Clear? So maybe I'll also look again. If anything I'll find, I'll let you know in next class. Yes, please. Why g of x is discontinuous? Signum of fractional part of x means you will get 1 when x does not belongs to z. It will be 1. Non-removable type. So in non-removable type, first finite type, it can be any two finite values, not only -1 to +1. So like in this case, both LHL and RHL are finite values. but LHL is not equals to RHL, right? So this type of discontinuity is also called as jump type discontinuity. So here the absolute difference between left hand limit and right hand limit is called as jump. How much it is jumping? The difference between left hand limit and right hand limit, absolute difference, is called jump. So you can take for example f of x is equals to greatest integer of x or fractional part, anything. So like this greatest integer of x, left hand limit at 0 you take, we have -1. Right hand limit at 0 you take, we have 0. So like now you can clearly see both are finite but not equal. There is like one unit it is jumping in the graph. Clear? So this is about finite type discontinuity. Now second one is infinite type discontinuity. So in infinite type, as I said, you can write here at least one of the limit approaches to infinity. If it is limit does not exist, we cannot do anything. We cannot reassign like f of a, we can modify. Limit we cannot do. At least one of LHL or RHL tends to infinity or approaches to infinity. Up. Oh, this one. So a small example for this we can take f of x is equals to 1 by x when x not equals to 0. So f of x is equals to 1 by x. Right hand limit will be approaching plus infinity. Left hand limit will be approaching minus infinity. Oscillating type. Definitely the limit value is finite, but it will be oscillating in between two finite values. So we can take example f of x is equals to cos 1 by x. If we take limit x approaches 0, definitely a finite value lying in between -1 and +1. But exactly how much it is, we are not sure. That's why it is called as oscillating type discontinuity. Am I clear? Any that's what in NCERT if you open the first line they'll write same thing only. If there are no breaks in the graph, then the function is no like the moment you are approaching infinity, it will be like the turns and all very sharp. If you see in the graph, like maybe here it is little trickier to draw. The moment we are approaching infinity, it is like and for every delta distance, it will be up and down, it will move. Clear? It is not at some finite value. Anything else? This is about oscillating type. Like I know this cos is some finite in between -1 to +1. But exactly the finite value I was not able to calculate. What I can say is it will be some value in between -1 and +1. That's only it is oscillating type discontinuity. Understood? Any doubt in this? Anybody? That's what, like if the moment we are approaching zero, the turns are like very sharp. It will be like going up and down in a very small delta distance at all. Clear? Understood? Now next, there is something called intermediate value theorem. Right? In if you remember, I think in this chapter, inverse trigonometry, I told like a function f of a and f of b having opposite sign, at least one root will be there in between a and b. So that is derived result from intermediate value theorem. What is this intermediate value theorem? Let's say we have a continuous function in a closed interval, and then like f of a and f of b are not equal, some different values. In that case, this intermediate value theorem says function attains every value in between f of a and f of b at least once. Clear? So this is for continuous functions. Put one small subheading. IVT is the shortcut. From this, the derived result is our location of roots theorem that we already used earlier in inverse trigonometry. So let's say function is defined from closed bracket a to b. So there are two conditions. First one is f is continuous in closed bracket a to b. Second one, like for our convenience, like if f of a and f of b are equal, there is no point of taking, there will be some value in between. Clear? That's only we'll say f of a is not equals to f of b. This condition can be broken, but like the above one cannot be broken. Clear? Even though if both equal, there are no values, no? Then there is no intermediate value. What about reading it? What we can say, then for every c belongs to f of a comma f of b, there exists at least one x naught such that f of x naught is equals to c. It says if there is some value in between f of a and b, that value will be attained by the function at least once. Now if we see in the graph, so some like this, one moment, let me change this one a little bit. So this is x is equals to a. Somewhere here we have x is equals to b. So like this side we have f of a. So this is f of b. So like in the interval of f of a and f of b, if I take some value, let's say this value I'm taking, right? This value must be attained by the function at least once. Clear? So if I draw one horizontal line, so we have 1, 2, 3. Clear? Understood? This is what intermediate value theorem is. Now from this only the derived result is location of roots, that we'll write as note point. Application of this one is what we use there. Can I scroll up? You guys wrote this statement and understood this one. If there is a continuous function in a closed interval, right, and f of a and f of b, some values, it may be maximum, minimum, doesn't matter, any two values you take. In between that two values, if there is a value, that value must be attained by the function at least once, right? Understood? Any other doubts? Now in note point, we'll write about location of roots. So first one, if y is equals to f of x is a continuous function in closed bracket a to b, and f of a into f of b is less than 0. F of a into f of b is less than 0 means both are having opposite signs. Then f of x is equals to 0 has at least one root in a comma b. See, like I can say that it may be 1 or it may be 3, it may be 5 odd number of roots you will be having in between a and b. This is what we applied. In that case, if you remember, it is a polynomial. Polynomial is a continuous function. We have proved it, it is increasing. And then once we proved it is increasing, it will be having only one root. That root we sandwiched in between two values and we set that root. Clear? Understood this one? This is called location of a roots theorem. And then like you can also add to this. So like let's take a continuous function. Quiet please. Special case of this one is what we have studied earlier. K0. Clear? K0 means 0 belongs to f of a comma f of b. F of a and f of b has opposite signs, has at least one root. This is about intermediate value theorem. Understood? Any doubts in this? Anybody? So I can say with this we concluded continuity of a function. Clear? Any doubts in this? Which one? First one. See, like maybe if I take graph, maybe you will understand better. Let's say you have a continuous function in a closed interval a to b. If you have a continuous function in a closed interval a to b, and we told that f of a and f of b has opposite signs. Let me take something like this. Right? So in this, I am saying here, this is x is equals to a, f of a is above the axis. And then like somewhere here, this is x is equals to b, f of b is below the axis. Now I can say in this case, f of a is greater than 0, f of b is less than 0. Function is continuous in a closed interval, and then function values at a and b are opposite in sign. Then there must be at least one root in between a and b. It can be 1, it can be 3, it can be 5, and so on. Odd number of roots we'll be having. Clear? See, like for polynomials, this is what we use. Polynomials is continuous functions, and then using this we will say. If both are having same sign, then we can have even number of roots in between. It can be 0, it can be 2, 4, 6, and so on. Clear? We won't divide that one. Any doubts in this? Anybody? All understood this? No doubts, right? So now let us see some problems on this? Hmm. Maybe one or two before going to differentiability. Let us find some easy problem. Hmm. Hmm. Wait. No, no, no. A and B are not close, no? Oh, here function is not continuous in closed interval. That's what you are saying. So in that case, what happens now? Maybe I can show you a situation. Function is discontinuous now at A and B. Let's take a function like this. This is A and this is B. So now let's say this is f of A and this is f of B. So if I say that there are so many values in between which function is not attaining. Am I clear? Understood this argument? So then I can see there is a problem, page number 60, problem 63. A good problem actually, this one. They are asking about discontinuity of composite functions. Don't worry, notes I'll upload in Teams by EOD today, end of the day. So page 60, problem 63. Anybody tried solving this one? If you solve also, you guys won't open your mouth. Page 60, problem number 63. Right, there is a function f of x and g of x given. Okay, what is f of x? F of x is a box of 2x square plus 1. So now what is g of x? G of x we have as 2x minus 3. This is when x is less than 0, 2x plus 3, x is greater than or equals to 0. So f of x is a greatest integer, g of x is a piecewise. As I said, if you are not good in greatest integer, fractional part, modulus, again one more thing, composition, that is the place where they are going to test you. Clear? So you have to be good in that, or else nobody can save you in continuity and differentiability. Now what I need to find? I need to find the number of discontinuous points for f of g of x. Clear? First let us find f of g of x. Clear? So what is f of g of x? 1 is an integer that I can take out of greatest integer or box. 2 times of g of x whole square plus 1. 1 won't do anything for continuity or discontinuity. 1 you can neglect as well if you want. Now this becomes box of 2 times of 2x minus 3 whole square. When one moment. Okay, x less than 0. 1 we should add only later. That's what I added. So 2 times of 2x plus 3 whole square plus 1. Right? So now notice this box. This box has no turning point in between -1 to +1. This box turning point is at 3 by 2. Clear? Understood? This box also has no turning point in between -1 and +1. Turning point is at -3/2. So like now we can eliminate when x is integer, maybe continuous thing. We can like when function is integer, maybe continuous argument eliminated. Right? Now what I will do, I'll count number of integers in this like so online students, can you hear me? So one more time I can say here, right? For this function, there are no turning points in the interval -1 to 0. Turning point is at 3/2. So like we can remove the argument even though function is okay. Came back. Can you turn on it? Uh, if you understand, you can try from there. Again at 0, we need to check because f of x is continuous at 0, g of x is discontinuous at 0. But the composition can be anything. We are not sure about the composition. Understood, na? Try then. Like maybe it will take some 2 or 3 minutes to turn on. That red light is blinking. Ajay, can you try again? Not sure. Green it came, huh? Let me talk with them. Don't worry. Like you try this problem. I'll bring somebody who knows. This one. Came out. Okay. Thank you, Ajit sir. Understood what we are going to do? So now tell me a range of this function when x is in between -1 to 0, then I'll tell you how many integers are there. See, like -1 less than x less than 0. I am trying to create this function. Forgot about one. So like what I should do, first I should multiply with 2 on both sides. -2 less than 2x will be less than 0. What I should do next, I think I should subtract 3 on both sides. -5 less than 2x minus 3 less than -3. Notice that if I do squaring, direction must be reversed. We have 9 less than 2x minus 3 whole square less than 25, right? So now I can multiply with 2 on both sides. 18 less than 2x minus 3 whole square less than 50. Count how many integers are there in this range at all those integers, like when 2 into 2x minus 3 whole square is an integer, box of that one must be discontinuous. We have only one thing, when it is a turning point, it may be continuous. Understood this? Any doubt? Right? See, I tried to create this function. For that, I have taken the range, multiplied with 2, subtracted 3, squaring on both sides, and then again multiplied with 2. Clear? So the range of this inside box, whatever you have, that is 18 to 50. If it is 18 to 50, how many integers are there in between 18 to 50? That many discontinuous points we will be having. Am I clear? Am I clear? Any doubts in this? How many integers are there? Can somebody count and tell me? 31, right? So this implies 2 times of 2x minus 3 whole square is equals to integer. We have, quite please, 31 points. Now in the same way, second one. For that, 0 less than x less than 1, same procedure again, multiply 2. No, 0 we need to check separately. We'll check separately. So now adding 3 less than 2x plus 3 less than 5, squaring if I do, I have 9 less than 2x plus 3 whole square is less than 25. 2 times 18 less than 2 times of 2x plus 3 whole square is less than 50. Now this function also has how many integers? 31, right? 2 times of 2x plus 3 whole square is equals to I. We have 31 points. So total 31 plus 31, 62 need to be verified at 0. Am I clear? So for a continuous, like for composition function, what actually I do, like in some situation I won't find composition, it might be trickier. In that case, I will use this definition at 0. Left hand limit will be limit x approaches 0 minus, we need to tell about f of g of x, so I write f of g of x. So I'll substitute 0 minus, this will be limit x approaches 0 minus f of g of 0 minus. In the left neighborhood of 0, what is the function value, or what is g of x when x approaching 0? In left neighborhood, how much is g of x? That is minus 3. Understood? Any doubt? That will be minus 3. So like, let me scroll up. Limit x is approaching 0 minus, this is f of 3 minus. I wrote 3 minus because it is a decreasing function till 3 by 2. From there only it is increasing. Clear? I think 3 minus, one moment, it is decreasing or increasing till 3 by 2? Decreasing, then maybe we should write 3 plus. How much is f of 3 plus? In the right neighborhood. Yes, please. That will be better in this case. First, we need to identify increasing and decreasing. So how much is that one? Limit x approaches 0 minus f of z of x will be equals to, so we have the function is a box of 2 times of 2x minus 3 whole square plus 1. So how much we get here? We get 2 into minus 2h minus 3 whole square plus 1. So now I am substituting 0 here. If I put 0 here, I have 2 into minus 3 whole square plus 1. So 2 into 18, 18 plus 1 is 19. What about right hand limit? 19 we are getting a. So then it is continuous.
தோசை ஊத்துறீங்களா என்ன? இன்னும் ஒரு தோசை.
Here it is Natarajan, you are very loud.
ஐயோ,
Please unmute. So if I put 0 here, I'm going to get 90. So now there are 31 plus 31, 62 points of discontinuity. So maybe again I'm giving you the quick glance. They have given a box greatest integer. They have given a piecewise function. They are talking about composition f of g of x. I found the composition. I have something like this. I have clearly checked it. There are no turning points in the given interval -1 to +1. If there are turning points, it might be trickier, right? So once I make sure there are no turning points, then what I can conclude here is like how many integer values this 2 times of 2x minus 3 attains, that many discontinuous points. Same thing for this one also. I found the range of 2 times of 2x minus 3. In the range of 2 times of 2x minus 3, we have exactly 31 integers. Here also we have 31 integers. Total 31 plus 31, 62 we have. Give me a moment. And then like at 0 also we check left hand limit and right hand limit. Both are equal. Function value is also 19 you will get. And then therefore it is continuous at 0. But like you have 31 points less than 0, 31 points greater than 0 where the function is discontinuous. Now what is your doubt? Why 30? Sorry? Yes. No, we won't get no. Like if you notice this is in different intervals. There is no common values in both the intervals. It is -1 to 0. When x is in between -1 to 0, function has 31 integers in the range. When x is in between 0 to 31, function has g class. Function has again 31 integers. So total 31 plus 31, if I do 62, at 0 I checked it is continuous, therefore 62 only. Anything else? Anything else? Any doubts? Copy this one, please. Hmm? Anybody writing this part over here? Anybody writing this part? Can I scroll up? Or say something, no? You are sitting like you don't know how to speak. Anybody didn't punch the ID card downstairs? Anybody didn't punch the ID card downstairs? Akshay Krishna is there, offline. Aparajita is there, offline. Online, not there. Please stay quiet. Any doubts? Can I scroll up? Okay. See, like I used left hand limit na, we use C minus H, 0 minus H. Checking the continuity at 0. Right? Minus 1 to 0 we checked, 0 to 1 we checked, at 0 we didn't check. Continuous. Anything else? I think this is break. You can go for break. Next should be math only. I'll talk and let you know. I want to take, like they should allow. They said exam or something they'll conduct. Don't know about it. What they planned. I should talk with them. Yesterday I'm not here. What happened? I don't. They conducted. You can go for break. Any doubts is there? You ask. I'll be here.